Pardon me. Good morning, class. Hope everybody's doing okay today. The Friday of the week that we're currently on. Got 3 more weeks of class, roughly speaking. Yay! Yes. Huzzah! Man, I am clipping terribly today. Testing, 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 testing. Testing, testing, testing. Testing, 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 testing. I wasn't even speaking particularly loudly then. Okay, maybe a little bit more. Test! Alright. Alright, cool. Anyway, so, we're kind of to an interesting point in this class. We are to the point where we have, roughly speaking, finished with C, the programming language. We are now going to begin talking about the next topic in the course, which is assembly programming. So, if somebody could just let me know that the chat's working, that would be fantastic. You know, I always like to make sure that the messages are actually getting through. I was just doing that out of paranoia until, like, excuse me, I think it was sometime last week it actually was the case that the messages weren't getting through, so, you know. If you guys don't mind, let me know if things are going on, etc., etc. So, there we go. So we're going to be going on to topic 9, assembly programming. So, this is a topic that I'm sort of piecing together from various sources, both previous sources that were included in previous offerings of this course and internet sources. I'm trying my best to present assembly programming in an approachable manner. Oh, good, we do have. Oh, good. There we go. Chat test. Thank you. I'm going to be doing my best to present this material in an approachable manner, because the problem with assembly programming, largely, is that it is difficult. It is difficult to do anything meaningful in assembly programming. It is difficult to do anything in assembly programming because it is very, very low-level programming. So we're going to try to get through this as best we can. We're going to be reasonable with our expectations of what we can accomplish in assembly programming. And, you know, hopefully nobody dies. The scope of the types of things that you can expect with respect to assembly programming are programs that would probably be no more complicated than the types of programs you saw in the first assignment for this class. It's probable that we're going to stay primarily within the realm of, like, these numerical examples which, you know, are basically, we're going back to such basic ideas. Okay. OBS seems to be indicating it's back up to regular signal strength. Let's see if... Are we back? Yep, looks like we're back. Okay. Apologies for that, folks. I have no idea what just happened. Cool. Yep, good. Excellent. Alright, yeah, would you believe me if I told you that over the summer semester I had that happening to me about once a week, and it was terrible because I only had 2 lectures per week, although they were 3-hour lectures each. So, I don't know, sometimes OBS just craps out, and I just have to bump the router, but anyway. So, assembly programming. Justice friends, assemble! For just a little while, we are going to be learning how to program assembly code. This is going to be a completely new thing for you guys, probably, even if you have a wealth of programming experience in other programming languages. It's improbable that at any point in your long history you've done any assembly programming whatsoever. If anybody actually does have any experience with assembly programming, I would love to hear about it in the chat. But somehow I think it's going to be new for most of you guys. So, if I expect you to program with assembly, it would be good if you knew what it was. When you are programming in assembly code, you are actually directly programming using the instructions provided by your CPU. Your CPU has an instruction set, and in assembly programming, you are using that instruction set directly with very, very few layers of abstraction between you and the bare metal hardware. Assembly is the lowest level language it is possible to program with while still using a CPU. Technically speaking, FPGA programming is even lower level, since you are programming circuits rather than instructions in pre-built circuits like a CPU, but FPGAs are well beyond the scope of this course, but you will see them in third year. FPGA stands for Field Programmable Gate Array, and those guys, they are programmed with a type of language called a hardware description language, which is a way of encoding electronic circuits as something resembling a programming language, which is then compiled to a reprogrammable circuit board that it essentially makes electrical connections based on the on what you've given it in the hardware description. But again, that's beyond the scope of this course. Because assembly language is so low level, there are very few mathematical abstractions available to you. You don't really get to not understand how the computer works. Like, when you're programming in something like Python, it's not strictly necessary to know how something like memory works. It's especially not necessary if you're using a really high-level language like Haskell. If you're programming in assembly, though, you not only need to know something about how memory works, you need to know the actual architecture of the CPU that you're programming for. At least in roughly you need to know what's going on in there. So, assembly programming in the real world requires an intimate knowledge of processor architecture. There are pages and pages of manuals that have to be memorized for you to be able to be an effective assembly programmer. It is a highly specialized skill. So let's talk about what a CPU is and what an instruction set is, since we're going to be programming in instructions. In general, a CPU executes instructions over data held in registers and in the The CPU executes instructions over the data which is held in registers, and those registers are in the CPU itself. The set of instructions which a CPU is designed with is known as the CPU's ISA, or Instruction Set Architecture. Sometimes this is referred to just as the architecture. The instruction set is the set of instructions that are available to you in assembly code. The instruction set architecture is the manner in which those instructions are implemented as electronic circuits. The instruction set is very, very important because it determines what operations occur in hardware and what operations occur in software. So you can imagine that you can have certain operations that are let me rephrase this. So let's imagine that we had a CPU that had only bitwise operations, right? Corresponding to the bitwise operations that we've learned for C. It would be possible to perform such operations as addition and subtraction using only bitwise operators, as we saw when we studied bitwise operators. However, it might be that addition is a sufficiently common operation that you would want to have dedicated circuitry in the arithmetic logic unit of your CPU to actually be dedicated to handling addition operations. if you want addition to be a natively supported operation of the CPU, it has to be in the instruction set. And so that's the difference between addition being done in hardware and addition being done in software. If you were to use it, if you were to perform addition using simpler instructions, that would be a software solution to creating addition. If you were to have dedicated circuitry for addition, that's a hardware solution for that. So when we are talking about assembly programming, we really are talking about the barrier between software and hardware. Assembly language is software, or assembly programs are programs. It is definitely software. However, you are making direct invocations of hardware. Maybe I'm beating a dead horse. ISAs are documented in very long specification documents, running into the thousands of pages in a lot of cases, these documents are maintained by companies like Intel and organizations like the RISC-V Foundation. Generally speaking, well, we'll get into it. Some ISAs are proprietary and others are open source. Those of you who are like big into the open source movement, RISC-V is the up-and-coming open source instruction set architecture, and Intel is the ancient Methuselah that everybody's trying to knock off of its pedestal, so to speak. While most ISAs can be relied upon to implement common features, such as arithmetic and bitwise operators, each ISA has its own assembly language. So there is not one assembly language like there is one C. There are many, many different assembly languages, essentially one for each instruction set architecture. So, if you have Intel assembly, that's called is this on the next slide? It's on 2 slides. Anyway, you've got it's in about 2 slides. We'll go through a couple of them. But first we have to understand the categories of ISAs. We've got CISC versus RISC architectures. Instruction sets are generally placed in one of 2 categories. We have CISC, or complex instruction set computers, and we have RISC, or reduced instruction set computers. Now, this is one of these funny little engineering trade-offs that you've been hearing about all throughout your engineering career so far, I hope. So, essentially, the difference between a CISC and a RISC architecture is that CISC machines have large sets of instructions. They support a large number of instructions. That's the basic, that's like the boiled down version. RISC computers have a much smaller set of instructions, i.e. the instruction set has been reduced. So that has some interesting consequences. When you have a CPU that has a lot of instructions, that means that the CPU itself has to have hardware to support the execution of all of the instructions that are in its ISA. That means that the CPU is very large, highly complex, and very expensive. By contrast, if you have a reduced instruction set machine, because the number of instructions is smaller, the amount of circuitry that is necessary to implement all of those instructions is also greatly reduced. This means that you have a less complicated processor that can be manufactured less expensively, because there's just simply less in it, right? Now, the trade-off there is that with a complex instruction set computer, you're actually you're leaving less to software and doing more in hardware. It moves it moves the hardware-software barrier up into the realm of software more. So more operations are done in hardware than in software, and because they're done in hardware, they can be done very, very quickly. Operations that would take many individual instructions in, like, simpler, how to say, operations which would take many simple instructions can be done in one instruction in a complex instruction set computer. And the other thing that is implicit in all of this that I haven't actually mentioned anywhere in the slides is when we're talking about instructions, generally speaking, a CPU executes one instruction per clock cycle. So when you have a CPU that's clocked at 3.2 gigahertz, that means that your CPU is executing 3.2 billion instructions per second. So that's what those numbers actually mean. So complex instruction set computers tend to be the older, well-established and proprietary ISAs. Think Intel and AMD. Reduced instruction set computers, these are sort of the up-and-comers. At least they used to be considered not as well established, but the mass deployment of smartphones has actually brought them into the category of actually starting to be competitive with the sort of high horsepower applications that you would typically find complex instruction set in computers in. Like desktops and supercomputers. Possibly also GPUs. So the reduced set, the RISC CPUs, these are, there are two main ones. One is ARM. ARM architecture is actually the one that we're going to be learning in this class, and ARM is the thing that runs basically all of your smartphones and tablets. The Game Boy Advance also ran on ARM architecture. Yeah. A smaller set of instructions means more functionality is left to software, but with the benefit of a far less complex processor. They are typical in mobile and embedded systems where expensive processors would be overkill. You can imagine if you were to build something, a typical embedded system like a kitchen timer or something, putting an Intel CPU in it that would ordinarily run a laptop, that would be complete overkill, right? Frankly, for a kitchen timer, you wouldn't even need a CPU. You could probably do it with an ASIC, but, you know, that's neither here nor there. Kitchen timers are my favorite embedded system example, so I'm not going to stray too far from it. Anyway, so here are some instruction sets, some instruction set architectures, which are used by various people for various things. x86-64 is the instruction set for 64-bit AMD and Intel processors. So, if you have a laptop that you are watching this on right now, it is highly probable that it is running x86. Windows, generally speaking, x86. Ubuntu is generally on x86 architecture, etc., etc. Computers in the proper sense. Used in laptops, servers, and other high-powered computers. ARM stands for Advanced RISC Machine. These are common in smartphone and tablet devices. And you also have RISC-V, an up-and-coming open-source ISA. So the thing about ARM is it's also proprietary. RISC, of the guys on this list, RISC is the only one that is open source. And because it's open source, what that essentially means is that a company does not have to license the ISA from another company in order to use the intellectual property that is the ISA to build a a processor according to that architecture. They can just download the file and build their processor using that specification. Because that is the case, there's this interesting and complex ecosystem of RISC-V projects that have been going on in recent years. RISC-V is actually a reasonably recent phenomenon. They only nailed down like the core elements and said, okay, we're locking the core elements, they're not going to change, so any implementation of these are going to be good. They only did that last year. So RISC-V is it probably hasn't quite found its niche yet within the market, but right now people are sort of working like mad developing these RISC processors to capitalize on a market that might hypothetically exist, because again, making it open source sort of opens it up more to a free market capitalism kind of approach with respect to processor design. Whereas, for a very long time, Intel and AMD had a oligopoly on the market. ARM came along, sort of knocked them off their pedestal a bit, but now it's more or less an oligopoly between AMD, Intel, and ARM. So RISC-V is hoping to sort of disrupt that oligopoly. So just as the C standard has a number of implementations, ISAs can have a number of assembler implementations, which all implement the same ISA to varying degrees. So x86, for instance, will have several different assemblers, just like C has several different compilers. Are there any questions so far? That's a lot of information. The microphone seems terrible. I'm gonna try the other one. Testing, 1, 2, 3, testing. Is this any better? Is this any better? Nope. Okay. Nobody's paying attention. Testing. Gonna have to turn it up a bit. Raise a little volume. Hello. Testing. Okay. I think I'll raise it a little bit more. Hello, there we go. Cool. Good. Okay, thanks. Yeah, okay. If the mic quality is really low, and it's annoyingly so, you guys could totally let me know, and I will try to do something about it. Anyway. So, let's talk a little bit about the life cycles of ISAs. To understand the differences between the ISAs on the previous slide, it is important to understand how they came about. In a lot of ways, the development of an instruction set architecture is similar to the development of a programming language. While an ISA may start small, over time things tend to get added to it, as the designers watch how the ISA is used. In the same way, a similar process to how long and short ints were added to C that we talked about some weeks ago. These are the types of gradual improvements that are made to an ISA over time. However, once an inclusion has been made, that inclusion tends towards permanency.
Removing features or instructions always runs the risk of invalidating the existing code base, and invalidating the existing code base is a thing that you want to avoid. You want to avoid at all costs if you're a manufacturer of chips. You can imagine, like, for example, if I was Intel and my next processor, the Core 78 or whatever, it was designed in such a way that 2 instructions were removed, and the Windows operating system used one of those 2 instructions somewhere important. Windows would not be able to run on my CPU. You think that maybe Windows might apply a little bit of pressure to me and then ask me, could you pretty please give us back that instruction? It's probable. And developing and releasing a CPU for Intel is like, I think the CPUs that Intel makes are like one of the most invested in products in the entire world, or something like in terms of the amount of money that it takes to produce one. But anyway, the end result is that over time, an ISA grows more and more complex, making the CPU larger and more expensive over time, though the added features do represent some degree of improvement. At a certain point, an ISA begins pricing itself out of the market with respect to certain applications, i.e., the processor in your laptop wouldn't even fit in the kitchen timer, let alone the power requirements and the expense. That's the other thing to keep in mind with a CPU, is that the more circuits that are in a CPU, the more circuits have to be powered, which means that the CPU, as the CPU grows, the power requirements for that CPU also grow correspondingly. So, this allows competing ISAs to come in and meet the needs of the market which has been abandoned by this now increasingly complex chip. As this new ISA gains users, there is an increasing pressure to include additional features and instructions, which drives up the cost, and the cycle continues. So, Intel got larger, ARM came in and scooped up a lot of the applications Intel was missing. Now ARM is getting pretty large, so RISC-V is coming in and scooping up a lot of the applications that ARM is missing. It's a cycle. So let's talk about actually programming an assembly code. In order to program in assembly, you have to unlearn pretty much everything you know from C and Python. This is going to be radically different programming from what you're used to. We are used to statements in a program being assignment statements, flow control, declarations, and other assorted things, like structs, etc. In assembly, each statement is a single CPU instruction. This means you got no assignment statements, no if statements, no while loops. None of those things exist. Although there's kind of an asterisk hanging off the end of that. While these things are not directly supported constructs of the language itself, it is certainly possible to reproduce the functionality presented by each of these things using assembly code. Obviously, since, C will eventually itself compile back down to assembly level instructions, CPU instructions, obviously everything here has to be, everything in C is possible inside of assembly language. It's a question of how much support that language gives you to be able to accomplish stuff. Even things like functions and symbolic variables are very different in an assembly environment. About the only concept that isn't radically different is pointers. Yay! We get to keep nothing except pointers. We are really out in the woods here. So, here's your survival kit. In this course, we are going to learn the rudiments of the ARM assembly language. It is highly probable that you will be trying out ARM assembly on a system that does not have an ARM processor. If you are going to be if you are programming assembly on a computer, then that computer is unlikely to have an ARM processor. It's likely to have an x86 64 architecture Intel or AMD processor. As such, it's impossible for you to natively run ARM assembly on your CPU. There are two options that you have here. Number one, you can try to set up a cross-compiler. Cross-compiler systems for ARM architecture do exist. However, the other option, which is the one that I'll be going with it for the course of these lecture slides, is emulation. Emulation is not a crime in this case. So what the emulator does is it's difficult to define what an emulator does without using the word emulate. It spoofs instructions. It creates a software environment where ARM architecture instructions can be executed as if they were being executed on an ARM architecture CPU, although the whole thing is in software and it's running on top of on top of an x86 CPU. Anyway, the one that I recommend, I haven't found a better one yet, but I haven't done a whole lot of looking, is Visual. There's a download link here. If you go here, it's got Windows, Mac, Ubuntu distributions. Probably the Ubuntu version will work on other Linux systems. There are some known issues, so just be careful of that. This is a project that has not been updated since 2015. It seems probable to me that it was some master's student's thesis work or something like that. But anyway, that's fine. It's good enough. It's not fantastic. This isn't anything like a tool that you would use if you were actually, doing work for a company programming assembly code. Not even by a long shot. However, it's a reasonably visual environment. It's got built-in debugging and step-through execution functionalities. So it's a good learning tool. We'll be able to get the rudiments of how assembly language works, but just keep in mind that this is kind of like a toy that think of it as a toy to play with. Emulator mimics a certain type of software, I think, or a certain type of ARM programming would be, yes. So mimic, it essentially it takes, mimic is a good term for it. So anyway, you may find that Visual lacks some features that you would expect. That's okay. It'll be sufficient for our purposes this semester. So, hello assembly world. Consider the following C code. Int total equals 0. For int I is 10, I is greater than 0, I minus minus, total plus equals I. The equivalent assembly code is as follows. Move R0, 0. Move R1, 10. Again, add R0, R0, R1. Sub S, R1, R1, 1. BNE again. This is what assembly code looks like. These are comments. The single line, the rest of the line comment in ARM assembly is the semicolon. Notice that semicolons are not necessary, strictly speaking. They are only necessary if you're commenting a line. And holy handbaskets of bleeding heck, do I recommend using comments in assembly code? Woof. Like 1 comment per line would be a good standard to reach. Although this particular piece of code doesn't reach that. So this is what the visual environment looks like. I actually have it open right here. So the buttons are kind of cut off because of the whatever it is, but if you put it in full screen mode, this is what you got. This is the same program. You can take a look at the history of each of these registers. You can step through your program. You can see these in either hexadecimal or in decimal. Step forward, step forward. You can click through. You can see the status of the status bits. And then you can see what happens when the emulation is complete. The results of this program are that the register R0 eventually acquires the value 55, and the R1 register eventually acquires the value of 0, although it counts down from 10 to 0. So there you go. That's an assembly program that has been run. And this is a demonstration of such, but in the slides. So let's break this guy down. Assembly programs are broken down by tab-separated columns. You can think of it like a table, right? So we've got the first column is labels, the second column is the instructions, and then you've got a list of operands. I've put all of the operands in separate columns in this particular instance, but if you go back to the assembly code itself, you'll notice that these are comma-separated lists, or comma-separated lists of operands. There we go. So we got a lot of stuff going on here. We're not going to talk about labels just yet. Those are related to control flow. Let's talk about what these instructions mean. So, the above example uses 4... Oop, I've got a question. I'll answer the question before I get into the slide. Schloop. Does white space indenting matter? That's a good question. Let's find out. No. Although it looks like it, wow, this emulator seems to have put everything back. Did it not save? Like, huh. Interesting. So I move that there. I save. Call it add.c. That's wrong, but whatever. Execute. Yeah, it just moves it back. Okay. I don't know if white space or indentation matters because the emulator I'm using automatically fixes my white space and indentation. So, yeah. Generally speaking, even if it doesn't matter, you should conform to the manner in which it's been laid out. That's 2 tabs for the label, 1 tab after the instruction, and then you get to do whatever you want. The instruction code. Interesting little bit of historical fact here. Way back in the ancient annals of history, when we were programming on giant room-sized computers like ENIAC, there were essentially before the invention of languages like Fortran or Fortran 77 or C or COBOL, all programming occurred in assembly code, and assembly code was often input into the computer in the form of punch cards. So back in those days, you didn't have these nice mnemonic instruction names. You actually had a table of opcodes that, rather than provide an instruction, you had to provide an opcode. And, there were just tables of opcodes, and you either memorized them or had to look them up each time. And then you had, the registers themselves would also have codes that you had to code in by hand. So everything was done with numbers in binary. However, when it was punch cards, you could, in fact, write on the punch cards without damaging the program itself, because the program was encoded in punches through a card, so you could write physically on the card, and it wouldn't interfere with the program. So you could comment things that way. But yeah, anyway. So let's consider the following. Let's consider the instructions that we're using here. We've got MOV, or move. Takes two operands, op1 and op2. Moves the contents of operand 2 into operand 1. Our C equivalent is op1 becomes op2. Now, you may remember me saying that we don't really have an assignment statement in that sense. The reason I say that is because op1, it is a mistake to think of R1 or R0 as being symbolic variables. They are not symbolic variables. These are not tied to memory in the RAM. These are registers inside of the CPU. They are a box that contains data that's embedded in the CPU itself. There's no symbolic jiggery-pokery going on here. So, yeah. We've also got the add operation. Takes three operands, 1, 2, and 3. Computes the arithmetic addition of op2 and op3 and stores it in op1. Your C equivalent here is op1 is equal to op2 plus op3. We've also got sub S. This computes the arithmetic subtraction of op3 from op2 and stores it in op1. This instruction is actually a compound instruction. So it is the instruction sub, which is just regular subtraction, plus S, where the S suffix indicates that the instruction also sets the status register. If you take a look inside here, this is the status register. So if we take a look through here, when we hit this, so this is essentially what's happening. R1 has got 0 in it. If we try to subtract 1 from 0, what we end up with is an overflow. So what sub S does is it sets the overflow flag here in the status bits. This overflow flag is then used by this instruction for control flow purposes. But that's what the S does. You can also add the S suffix to an add operation to check for overflow related to an addition operation. So the equivalent C code for sub is op1 is equal to op2 minus op3. And I think that's our time for today. Thank you very much for your time and attention today, folks. This has been a very rough introduction to assembly programming. We will get into it a bit more as time goes on. I'm thinking that the way that we'll do this is we'll have, it'll be primarily example-based, because I think that's like easier. But, yeah, anyway, I'll stick around for a little bit yet to answer any questions that you guys may have. But other than that, cool. Alright. Seems nobody has any questions. So, yeah. Take her easy, folks. See you on Tuesday.